Okay, so the first one is really a review of the last lesson. It says describe the transformations, then state the restrictions, and then graph it. So this is really a continuation of what we just did. So I'll give you a few minutes to work on that.
Okay, I'm going to use abbreviations here. Faster. So, vertical stretch by 2, reflection, and x-axis, vertical translation 6 up, horizontal translation 3 right.
Okay, so on a test, you're not going to short form it. Okay, I did there, save space. Here, we know our vertex is 3, 6. So 3 for x, 6 for y. Okay. Hopefully it has been reflected because there's not enough grid paper if you're going up from there, right? So then think about it. So normally, for 1 unit over, you go 1 up. So now from a vertex, 1 unit over, I'm going to go 2 down from there because it's been stretched by 2 and then reflected. Normally for 4 units over, I go 2 up. If I stretch that by 2, it's 4. Reflected is -4 from there. So from the axis of symmetry, basically. So if I go 4 units to the right, then I'm going to go 4 units down from there. Normally, 9 to the right of the vertex is 3 up. So now it would be 6 down. 9 to the right of the vertex would be 3, 6, 9. And I'm going 6 down, 3, 6. And then, really, I don't have space to do another nice point. So now I'm going to join these up. Make that a little clearer there. Arrow on this end, but not on the other end. Okay. So by stating the restrictions on the variable, it means what values of x make it defined. So really, for radicals, we're not saying what doesn't define it. We're actually saying for what it is defined for. So almost like it's better to say the domain. Okay. So in this case, we know x has to be greater than or equal to 3. And that really comes from this, right? We have to take square root. That radicand has to be greater than or equal to 0. Okay. So we've already graphed it. Domain and range in the function. So again, that comes from what we just did here. So the domain proper form will be x greater than or equal to 3. And then the range, so the y value at the range, if you didn't have the graph, you know you have to have y and 6. Right? So the y value at the vertex is 6. If it is, the leading coefficient was positive, then it would be everything greater than or equal to 6, but it's negative. It's been reflected, so it's less than or equal to 6. So then it says use the graph to find the value of x when y is 2. Show it on the graph. So when y is 2, you go across to there and down. So that's 7. Okay. If you were doing it graphically on your calculator, you graph the original, you graph y equals 2, and then you intersect those two graphs. 6 says solve that equation algebraically. So notice the similarities. The left side is the same as the graph. The right side is 2. That's what we just graphed, basically. So algebraically, it gives you a hint. First, isolate the radical, and then square both sides. So here, we want to get the 2 to the right. Then we want to divide by -2. Okay, and then to get rid of the radical sign, we have opposite of square rooting is squaring. So we want to square both sides. And then add 3. Okay. So that's a proper algebraic solution. How does it compare to your answer in question 6? Well, it was the same. When we went across from y equals 2 to the graph and then down, we got an x value of 7. Okay, now next one, solve same left side of the equation, but now equal to 0. So we're going to bring the 6 to the right, or you could bring the radical to the right, then divide by 2 or -2, depending on what you did. Okay, and so square both sides, and we get x equals 12. Take a look back. So really, this was our function that we graphed. And so we're saying when y is 0, what's x? So that's the x-intercept. So if we go back to look at our x-intercept here, we get 12. So we get the same thing when we do it algebraically. Okay. In these cases anyway. So then, can you find the same answer to question 8 just by looking at the graph? Yeah, we just did. Show the answer on the graph and explain how you use the graph to find the answer. So you're looking for a point where y equals 0, which is the x-intercept on the graph, which is 12. Okay, next one, very similar. Now it's equal to 8. So we're bringing 6 over. Divide by -2. Square both sides. And that gives me x minus 3 equals 1. So x equals 4. Okay, when you go to verify this, you'll notice it doesn't work. If you look at your graph, you'll see why. This is saying that our graph, we're looking for a point on our graph where y is 8. There are no points. Y is 8 would be up here. This graph goes down and to the right. It never goes back up. So when we solve this algebraically, we get what's called an extraneous solution. Okay? So there are no solutions to this. And so if you check algebraically, remember to verify, keep your sides separate. This would be -2 times 4 minus 3, square rooted, plus 6. Right side is 8. So you get 4 and 8 there. Left side is not equal to the right side. Okay? So if you verify, so sometimes you'll solve algebraically, you'll get a solution. You do need to check it. It could be extraneous. Okay? And in this case it is. So what happened in question 11? Did your check work? Nope. Refer to the graph and explain why the answer is incorrect. So from the graph, there is no point on the graph with a y value of 8. So why does that happen? Well, remember what we're doing, we're squaring something with x in it. So even though it's square rooted, when we're squaring, it's actually introducing another possible root. Ends up there's only one root when we solve it, but it's extraneous. Okay, so there wasn't anything to start with. So sometimes when you square both sides of an equation, it introduces a solution that it ends up being extraneous. So just be aware of that. So, and there's the definition, basically. An extraneous root is a solution that is found algebraically, but that does not verify the equation when you check using substitution. Extraneous roots are common in radical equations and must always be rejected. In an equation, if an equation has only extraneous roots, then it has no solution, just like that last one. Kind of like if we, when we check for non-permissible values, when we're doing rationals, that we may have got a solution, checked our non-permissibles, ended up being a non-permissible value, so we eliminated it from our solution set. It was extraneous. Okay. Inadmissible roots, that is a root that satisfies algebraically, but doesn't make sense for an application question. Extraneous means it's extra. It doesn't work. Okay, and then solve the following radical equations. So we'll do these two, and then we'll stop for today. Okay, so same deal. You want to get that term with x in it by itself, just like always. That means try to isolate the radical term. So I'm going to bring the 6 over. And then I'm going to divide by -3. Then you're going to square both sides. And then bring the 4 over. So that's 53. It says show a check. If it doesn't say show, then you could do it in your calculator or in your head. But it does say show. So always go back to the original, never an intermediate step. So what's that? 6 minus 3 times 7, which is 21. So that's -15. which is the right side. Okay, so that is the solution. Okay, go back and put your solution brackets around it or box around it or whatever. Make it clear that if there are extraneous, you cross it out. And then rewrite what the proper solutions are. Okay, then try the next one. You might notice right away here. So I divided by 2 because I wanted to get the radical by itself. This is a positive root. The number outside is positive. This is never, if this is negative, you can't take the root of it. So whatever x is will give you a positive number. How could that ever give you a negative? Or can it? No, right? There's nothing you could put in there that would make this positive root negative. So you could stop right now and say no solutions. If you solve algebraically, then you would square both sides. And you get x equals what? Okay, then you need to check. So 2 times 1 plus 3 is 2 times root 4. 2 times 2 is 4. Our right side was negative 4. Left side is not equal to right side. So this is extraneous. Therefore, no solutions. Okay? So if you had seen that right away, that this was a positive root equaling a negative number, no x's, because if there's x's over there, maybe it could be positive, there's no solutions to that. Okay? Algebraically, you do get one, but obviously it's extraneous because it doesn't make sense. Okay, so make sure you do that check. So that's where we're going to stop for today.